Good afternoon, everyone. My name is Kuldeep Meel. I'm at National University of Singapore. I'm going to discuss our work on sparse hashing for approximate model counting. This is joint work with Akshay from IIT Bombay. As you can see, we decided author order randomly, and Akshay and I are still friends. Okay, so let's get started with one of the most fundamental problems in computer science of Boolean satisfiability. Where given a Boolean expression using operators such as AND, or NOT, the question is there a satisfying solution or an assignment of zeros and ones to the variables that make the expression evaluate to 1? We are typically interested in formulas represented in conjunctive normal form, where we have a set of clauses, all of them are connected by AND. Inside every clause, we have variables or their negation. And if we stare at this expression long enough, I hope you will agree with me that assigning x1 and x2 to 0 and x3 and x4 to 1 would make this expression evaluate to 1. Of course, as we know, set is NP complete, and despite intense work over almost 5 decades, we still do not know if P equals to NP or not. In some sense, this is usually told a story where we have not made much progress in resolving or being able to find an efficient algorithm for set. But at the same time, something else has been brewing in the field of formal methods and artificial intelligence. And this is the story I would like to tell you, the tale of triumph of set solving. And I would quote Don Knuth, who recently wrote an entire book on set solvers, and he put it very nicely that today's set solvers are able to handle problems that were regarded as hopeless just about a few years ago. As we speak, the solvers find application in a wide variety of areas, ranging from model checking, G3, noise analysis, and planning, and so on. So at this point, one can claim that now that set is easy. Of course, the easy comes with qualification. I do not mean to claim that set is easy for every instance out there, but we repeatedly see that the problem seems to be easy to solve for instances that arise from practice. The distinction between not every instance being amenable to set solvers is going to be crucial in our work, as we would not like to treat the solvers as oracles, but as solvers whose performance depends on kind of instances we give to them. But taking a step back, assuming by claiming that set is easy for most of the practical instances, a natural next frontier of problems to look at is problems beyond NP. And I'm going to focus on one such problem, which is the focus of our work, is of model counting. So again, to take a step back, we started with a set of Boolean variables. We have a formula of these variables. Let the sol of f be a notation to indicate the set of solutions of this formula. A solution is a satisfying assignment of this formula. To make sure we are, and the problem of model counting in this case is to determine the cardinality of the set, which is to determine how many satisfying assignments the formula has. To make sure we are on the same page, let me give a quick example. Let's say the formula is x1 or x2. In that case, the set of solutions of this formula is essentially all the assignments to x1, x2, except 0, 0. And now the problem of model counting would be to estimate the cardinality of the set of solutions of the formula, which is indeed 3. By seminal work of Choda in 1989, we know that the problem of model counting is sharply complete. This hardness also manifests in practice, and often we are interested in epsilon delta approximations. In particular, to formally state, we are interested in designing a subroutine, let's say approx count, that takes a formula epsilon delta as input, and the estimate written by approx count is within 1 plus epsilon factor of the exit count with probability at least 1 minus delta. Well, at this point, one might say, why should we be interested in the problem of model counting? Apart from it being a fundamental problem in theory, the problem has several applications in a wide variety of areas. Due to lack of time, I'm not going to focus on these applications, but I would like to invite you to our paper to find more about different applications of counting. Since there are so many applications of counting, it is no surprise that there has been a lot of algorithmic work on designing efficient techniques for model counting. The early work fell into two ends of the spectrum. On one end, we had techniques that had very strong guarantees but often poor scalability. On the other end, we had techniques that had big guarantees but impressive scalability. Over past decade and a half, there has been a lot of effort in what is generally known as the hashing-based approach, which promises scalability and also rigorous guarantees. The origin of this work goes all the way back to Stockmeyer's seminal work in 1983. To put our contributions in context, I am going to quickly review the core ideas behind hashing-based approach. Essentially, let the circle be the space of all possible assignments and the dots represent satisfying assignments. Since we have access to powerful set solvers, one way could have been, well, we can use a set solver to just enumerate all the solutions. That's not going to work because the number of solutions can be really large, easily of the order of magnitude of 2 to the power 100, so we won't be able to make so many calls. In that case, wouldn't it be nice if we could partition the space of solutions into cells that are roughly equal and the number of solutions in the cells is small enough that you can use a set solver to enumerate all the solutions in a cell. If we can do such a partitioning, then the algorithm for counting is fairly easy. We pick a random cell. Since such cells are small, we can enumerate all the solutions in the cell, and then all we have to do is to multiply with the total number of cells. You can see a primary challenge such a technique has to address is, well, how are we going to partition into roughly equal small cells of solutions without knowing the distribution of solutions? To address this challenge, the typical idea is that we are interested in designing a function that maps assignments to cells. In typical computer science context, we are looking at a hash function. Once we have access to such a hash function h, then solution in a cell alpha is just the conjunction of the solutions of the formula conjuncted with all the assignments that h maps, all the assignments y that h maps to alpha. And the key idea here has been that we consider a large enough family of hash functions so that if we choose h randomly from this large family capital H, then such a hash function is going to be able to partition into roughly equal small cells with a high enough probability. In particular, the techniques use the key idea of pairwise independent hash functions. So let me formally define pairwise independent hash functions. So let H be the family of two wise independent hash functions that map from space of assignments over n variables to cells that can be represented by m bits. So what such a family ensures? It says that for every pair of assignments and any two cells, if we pick a hash function randomly from this family, then the probability H maps y1 to alpha 1 is same as probability H maps y2 to alpha 2, which is 1 over the number of cells. Furthermore, these events are pairwise independent. In particular, probability H maps y1 to alpha 1 and H maps y2 to alpha 2 is just the product of marginals. What does these pairwise independent hash functions give us? Well, in particular, we are interested in this random variable gn, I'm using, which indicates the number of solutions in a randomly chosen cell. I'm using m to denote the fact that we are hashing the space of assignments to cells that can be represented by m bits. So the expected number of solutions here would be just the total number of solutions divided by total number of cells. Furthermore, the variance is small. In particular, variance is less than expectation. In all these techniques, we are going to be often interested in the ratio of variance to expectation, which is also known as dispersion index, and we can rewrite this observation to say that the pairwise independent hash functions ensure that this ratio is less than or equals to 1. Why do we care about this ratio? Well, this ratio crucially determines the definition of small cells. So we define small cells as a cell that has the number of solutions roughly of the order of magnitude of the dispersion index times 1 over epsilon square. Remember, since we are going to be using a set solver to enumerate all the solutions in a small cell, we would like the dispersion index to be small enough so that we don't have to enumerate too many solutions. Okay, so what we are doing, we are going to use a pairwise independent hash function. So at this point, let me quickly discuss where are these pairwise independent hash functions. So I'm going to discuss the standard construction, which essentially constructs the such hash functions over variables x1 to xn. Remember, we have n variables. To construct a hash function mapping over m bits, cells that can be represented by m bits, we choose m random XOR. How do we choose every XOR? Well, we pick every variable with probability half and we XOR them. So a quick observation here is that if you are picking every variable with probability half, then the expected size of each XOR is n over 2. To pick a cell randomly, we set each of these XORs to 0 or 1 randomly. And now the solutions in a cell is essentially conjunction of the original formula conjuncted with these m random XORs that we have constructed. At this point, we rely on the power of set solvers. We give this formula to the set solver and ask it to enumerate all the solutions in a small enough cell. Well, remember, the solvers are not oracles. So their performance depends on the kind of formulas we give to them. And a consistent observation has been that the performance of the set of our set solvers degrades with increase in the size of XORs. We are interested in handling formulas involving hundreds of thousands of variables. In such a case, expected size of each XOR will be of the same order of magnitude, and the set solvers cannot handle such large XORs. This distinction between that the solvers are not oracles is very crucial for development of techniques that can handle instances in practice efficiently. So how do we try to address this? One way could have been, well, instead of choosing every variable with probability half, why not we choose variables with probability smaller than half? Let's go along this train of thought. So suppose we pick every variable with probability p, then of course the expected size of each XOR is just n times p. So if p is small, we are going to get smaller XORs. So what does these XORs give us? Turns out we can still show that the expected size of the number of solutions in a randomly chosen cell is still total number of solutions divided by total number of cells. But the story of variance gets complicated. In particular, variance of GM is now less than expectation of GM plus this additional factor. So let me try to go over this additional factor. So what we are doing, we are summing up over all pairs of solutions of the formula, where we use W to indicate the Hamming distance between these solutions. And then for each of these pairs, we have to multiply with a term, which is R of WM. So R of WM looks like a bit of a complicated expression, but the key thing that I would like you to notice is that as P gets smaller and smaller, this expression, this is indeed gets larger. So this is monotonic in P and also in W. In case of W, as W gets larger and larger, the R of W decreases. So when P is half, then fortunately we don't have to worry much, because 1 minus 2P is just 0, and then the entire expression for R of WM turns out to be 0. In such a case, variance is indeed less than expectation, or the dispersion index is bounded by 1. So if we want to pick with probability P less than half, then we need to look at ways of being able to bound this expression on the right. And this is what for last decade and a half, there have been several attempts that tried to do. Let me try to capture the core idea of these attempts. Essentially, we are trying to bound this expression, which is summing over the pairs of solutions. So we can rewrite it to say that let me sum over all the solutions of the formula, But corresponding to every sigma 1, I'm going to say that, well, how many solutions can be a distance W from a fixed solution? Since we have, we are looking at a Boolean hypercube of n dimensions, because we have n variables, there can be at most n choose W solutions that are at distance W from it. So in that case, we can upper bound it by n choose W, and we can then try to use several analytical techniques to get derive stronger bounds here. The key issue with this approach is that n choose W grows really fast with n. So it has not been possible to upper bound the dispersion index by a constant. And remember, the dispersion index determines what can be called as a small cell. So if we are not able to bound it by a small enough constant, then we are stuck with these very large cells, and we would spend a lot of time enumerating all the solutions in these cells. So it turns out, contrary to what we would have expected, if we use the bounds derived by these techniques, then we observe about 100 to 1000 factor of slowdown. So how do we try to address this? The key observation underpinning our work is to say, well, we can try to rewrite the same expression in a different way, which is to say that what is this trying to capture is that we are summing over all pairs of solutions of the formula. So let's try to club together all the solutions that are at distance W, and we can sum over from W from 0 to n. So CF of W indicates all the solutions of the formula that are at distance W times R of WM. Distance again is Hamming distance. Okay. And once we rewrite the expression that I have shown on the right hand side, we can try to say, how can we bound CF of W? And this is where we rely on very exciting work recently by Rastian and Renault. And we are able to upper bound CF of W, this entire expression here, where for each of these terms CF of W, we can bound by AT square root NL choose W. In particular, what is the, where L is the log of the number of solutions of the formula. So what's the improvement we are able to see? Well, we are able to improve from n choose W to AT square root NL by W. So if we take the ratio of these two, then essentially what we get is n over L to the power of W by 2. Typically, L is smaller than n, much smaller than n. So I can see an exponential improvement in these bounds. This exponential improvement we can formalize, and what we can show is that, well, if the number of solutions can be upper bounded by, let's say, some constant k times 2 to the power n, then it is sufficient to pick XORs where every variable is picked with probability p, which is as of log m by m. And then the corresponding XORs that we have constructed, they ensure that the dispersion index is upper bounded by q, a small constant. Q can be chosen arbitrarily as long as q is greater than 1. So at this point, recall that the average size of each XOR is just n times p, because we are going to be picking every variable with probability p. So we are able to improve from, we were initially picking every XOR with probability half, which I can rewrite to say that m by 2 over n. Now we are picking over log m by m. This looks all nice, but at this point, one has to start wondering, how are we going to use this theorem for our algorithms? And in particular, do we have any meaningful bounds on the number of solutions of the formula? Remember, the number of solutions of the formula is what we set out to determine in the first place. So we are going to take a step back and try to understand how these hashing-based techniques work. So the idea is that we would like to partition into the number of cells so that all the cells have roughly threshold many solutions. And since we don't know in advance how many solutions are there, so we try for each value of m. At every point, we pick a random cell and we ask, is the number of solutions less than or equal to threshold? Let me illustrate it more graphically. We start with the formula. We ask, is the number of solutions less than or equal to threshold? You can answer this query by just asking for up to threshold plus 1 solutions from a set solver. If the answer is no, then you partition into 2 cells, you pick one of them randomly, and you again ask the same question, is the number of solutions less than or equal to threshold? We keep doing it until we reach a point where the number of solutions is indeed less than threshold, and the estimate is total number of solutions in a randomly chosen cell times the total number of cells. So, well, how does this allow us to obtain any meaningful bounds on solutions of F? And our observation is that if you look at the working of this algorithm, you probably don't even need to get bounds on solutions of F. Why so? Again, the random variable we were interested was the number of solutions in a randomly chosen cell after m XORs. And recall here, we are slowly adding more and more XORs. So the analysis of these techniques can be made to work. So a core observation that we made in our work is that this analysis can be made to work as long as you can ensure that the dispersion index is bounded by a constant Q whenever solutions of F is upper bounded by threshold times 2 to the m. Remember, the algorithm makes no assumption about the upper bound on the number of solutions, but the theoretical analysis only requires bounding of the dispersion index under this assumption. And then the entire analysis can handle any possible formula out there. So what does this give us? Well, when we are putting the mth XOR, we can choose the variables in this mth XOR with probability Pm, which is of log m by m. Let me illustrate it more pictorially. Here is what our hash functions look like. So on x-axis, I have listed the number of XORs, and on y-axis the PM. So as you can see, the green is the set of the probability corresponding to every XOR, and the red is trying to capture the behavior, which turns out to be log m by n. So as you can see, as we add more and more XORs, we add sparser and sparser XORs with smaller and smaller probability. So this is very interesting and different from what earlier attempts had tried to do. So instead of choosing the entire matrix with very sparse XORs, what we get is that as we add more and more XORs, every subsequent XOR that we add is sparser and sparser. We call our hash family as HREN, alluding to the place where we initially started work on this problem. And these are the sparse hash functions that can ensure the family that for which I just described, ensure that the dispersion index is upper bounded by a constant 1.1. Okay, so that was the theory part. How does it affect in practice? Well, let me show you the experimental evaluation. So we took the state-of-art approximate model counter approximc4. We integrated approximc4 with our hash function scheme. We call it approximc5. Here are the experimental evaluations. So we have set of benchmark variables. This is the log of the count written by our counter. And here are the times for approximc4 and the times for approximc5 and the speed up, which is the ratio of the time of approximc5 divided by time of approximc4. So a few observations are in order here. First thing, for some of the benchmark, we do see that there's a slowdown. Why so? Because remember, the threshold depended on the dispersion index. So if you are just using two wise independent XOR, then you had XORs that are dense, has lots of variables, but at the same time, you had to know the size of these cells is small. So this factor of 1.1 does make the cells to be slightly larger. So in cases where you are not adding a lot of XORs, then the gains that you get from sparse XORs don't translate into the speed up because of the cons of having to work with larger cell. But then as we work with formulas having lots of solutions, so log of the count is essentially the number of roughly the number of XORs we are going to be putting. So with the formula that has lots of XORs, we are going to be putting a lot of, the formula that has lots of solutions, we are going to be putting a lot of XORs. In such cases, it indeed turns out that we can see a significant improvement in the runtime performance. One thing we would like to highlight is that, to the best of our knowledge, this is the first sparse XOR-based scheme that can achieve speed up without loss of theoretical guarantees. The algorithm Approximate 5 still has the same epsilon delta guarantees as that of Approximate 4. So with that, let me conclude. I discussed our work on hashing-based techniques, and I will sketch out quickly two future directions. One is from more theoretical aspect, which is if we can try to obtain lower bounds on the sparsity of XORs. From algorithmic aspect, we would really like to be able to achieve speed up without slowdown for any instance. Let me conclude the talk by pointing out the tool is open source. I would like you to try it out. With that, thank you very much for listening to the talk.